A planet appeared beside the closest sun-like star to Earth, and then it vanished. Not metaphorically, not gradually. It was there in the data, a faint point of warmth glowing beside Alpha Centauri A, and months later, it was gone. No explosion, no dramatic cosmic event, just absence. 4 light-years from Earth lies a system we have stared at for generations. In the scale of the Milky Way, that distance is almost nothing. The galaxy stretches 100,000 light-years across. Most of the stars we study are so far away, their light began traveling toward us before human civilization built its first cities. But Alpha Centauri is different. If the Milky Way were the size of North America, Alpha Centauri would be on our street. It is not an abstract destination. It is our neighbor. And yet, for decades, it refused to answer a simple question. Does it have planets? The irony was almost cruel. By the early 21st century, astronomers had cataloged thousands of exoplanets orbiting distant stars. We found massive hot Jupiters skimming the surfaces of their suns. We found compact systems packed tighter than Mercury's orbit. We found rocky super-Earths and mini-Neptunes and worlds so strange they defied every model we had built. But not here, not around the star next door. Alpha Centauri remained silent. Part of the mystery lies in what Alpha Centauri actually is. It is not a single star, but a gravitational partnership. 2 sun-like stars, Alpha Centauri A and Alpha Centauri B, orbit one another in a slow 80-year dance. A third, smaller red dwarf, Proxima Centauri, circles far beyond them. Alpha Centauri A is especially tantalizing. It is almost a twin of our Sun, similar in size, temperature, and age. If planetary systems form commonly around stars like ours, then Alpha Centauri A should be an ideal host. It should. But nature does not always cooperate with expectation. Binary stars complicate everything. When 2 massive bodies orbit closely, their gravity stirs the disk of gas and dust from which planets form. Imagine trying to build a fragile sandcastle while 2 shifting tides tug from opposite directions. Theoretical models once suggested that stable planets in such systems might be rare, or at least difficult to detect. And then there was the brightness. Alpha Centauri is the 3rd brightest star in our night sky. That brilliance inspires poets. It frustrates astronomers. Just telescopes designed to find faint planets operate like cameras tuned for candlelight. Point them at something too bright, and the detectors saturate. Light scatters. Diffraction patterns explode outward. Any small companion nearby is drowned in glare. Finding a planet beside Alpha Centauri is like trying to see a firefly against a searchlight. For decades, astronomers tried anyway. They searched for tiny stellar wobbles, the gravitational tug of orbiting planets. They monitored dips in brightness, subtle shadows cast as worlds passed in front of their stars. There were hints. A possible Earth-mass planet around Alpha Centauri B was announced in 2012, only to later dissolve under reanalysis. Signals rose, then fell. Hope became caution. Meanwhile, discoveries elsewhere multiplied. NASA's Kepler mission revealed something extraordinary. Planets are not rare. They are common. Nearly every star likely hosts at least one world, which made Alpha Centauri's silence even stranger. How could the nearest sun-like system be empty? The question was not merely scientific, it was emotional. For over a century, Alpha Centauri has occupied a special place in our imagination. Science fiction writers chose it as humanity's first interstellar destination, not because it sounded exotic, but because it was reachable, at least in principle. If we ever learned to cross the vast darkness between stars, Alpha Centauri would be our first harbor. But what kind of harbor? A barren system of stars offers one story. A system with planets, perhaps even habitable ones, offers another entirely. When the James Webb Space Telescope launched, something changed. Webb was not just another observatory. It was the most powerful infrared telescope ever built. A machine engineered to peer backward in time, to study galaxies formed shortly after the Big Bang. Its golden mirrors were designed to collect the faintest whispers of ancient light. It was optimized for darkness. Alpha Centauri is the opposite of darkness. Pointing Webb at such a bright star was risky. The telescope's detectors are delicate and irreplaceable. Too much light can overwhelm them. Observing Alpha Centauri required extreme caution, and a technique known as a coronagraph. A coronagraph is, in essence, an artificial eclipse. Inside the instrument, a tiny mask blocks the central starlight, suppressing the glare so that faint objects nearby can be seen. It does not eliminate the light completely. That is impossible. But it reduces the overwhelming brilliance enough to reveal companions thousands of times fainter. Instead of searching for reflected light, the glimmer of a planet shining in visible wavelengths, Webb would search for heat. Planets glow. Even cold worlds emit infrared radiation. A mature gas giant orbiting a sun-like star absorbs stellar energy and re-emits it as warmth. At certain wavelengths, especially around 15 micrometers, that faint thermal signature becomes detectable. Webb's mid-infrared instrument, MIRI, was designed for exactly that range. If a Saturn-like planet orbited Alpha Centauri A within a few astronomical units, MIRI might catch its glow. But everything had to go perfectly. Well, Alpha Centauri moves rapidly across the sky due to its proximity. Its position shifts measurably over time. Even a tiny miscalculation, smaller than the width of a human hair seen from kilometers away, could cause the star to misalign with the coronagraph mask, flooding the detector with unwanted light. So, the observing team did something unusual. They did not point directly at Alpha Centauri. Instead, Webb locked onto a nearby reference star, dimmer, manageable, stabilized itself, and then executed a precisely calculated blind offset, shifting its aim by a predetermined amount to place Alpha Centauri A behind the coronagraph. It was a maneuver that demanded extraordinary precision. Then they waited. In August 2024, Webb stared for hours. Infrared photons that had traveled for more than 4 years through interstellar space struck its mirrors and flowed into its detectors. Data streamed back from the telescope's distant perch near the second Lagrange point, 1 million miles from Earth. The raw images were chaos. Diffraction spikes radiated outward. Scattered light from Alpha Centauri B streaked across the field. Noise patterns overlapped in complex swirls. To the untrained eye, it looked like abstract art. But astronomy is not about first impressions. It is about subtraction. The team applied reference star differential imaging. They observed other stars under identical conditions to model how Webb behaves in the absence of planets. They subtracted those patterns from the Alpha Centauri data. They removed correlated noise. They analyzed independent subsets to check for consistency. Layer by layer, they peeled back the glare. And then they saw it. A faint, steady point of infrared light. It sat approximately 1.5 arcseconds from Alpha Centauri A, about 2 astronomical units in projected separation. Not blazing, not dramatic, just a dim spark roughly 10,000 times fainter than the star beside it. But statistically, it was strong. The signal reached significance levels high enough to rule out random noise with extraordinary confidence. Something real had left its imprint. They gave it a neutral name, S1. Not planet, not yet, just Source 1. Based on its brightness in the mid-infrared, its estimated temperature fell between 220 and 250 Kelvin. around -50 degrees Celsius. Cold, but consistent with a mature gas giant warmed by a sun-like star at that distance. If the modeling was correct, S1 could be a Saturn mass world orbiting Alpha Centauri A, a billion-year-old planet, around the closest sun-like star to Earth. It would be the nearest directly imaged exoplanet candidate ever detected. But before excitement could overtake caution, the team did what scientists must always do. They tried to destroy their own discovery. Could it be a background galaxy aligned perfectly along our line of sight? They checked catalogs. Nothing known occupied that position. Could it be an asteroid drifting through our solar system? Solar system bodies move relative to background stars. S1 did not shift during the observation window. Could it be an instrumental artifact? A speckle masquerading as a planet? They injected artificial planet signals into the raw data to compare behavior. S1 matched real signals more closely than noise. It survived every internal test. And yet, one rule remained absolute. Planets move. If S1 truly orbited Alpha Centauri A, it would not remain frozen in place. It would trace an arc along its orbit. Over months, its position would shift in accordance with Kepler's laws. Motion would be the proof. Follow-up observations were scheduled for early 2025. If S1 reappeared, even slightly displaced, the case would strengthen dramatically. If it failed to appear, then something far stranger would unfold. Because planets do many things. They orbit, they shine, they cool, but they do not simply vanish. And yet, that is exactly what would happen next. They went back. In February 2025, the James Webb Space Telescope turned its golden mirrors toward Alpha Centauri A once more. Same star, same instrument, same coronagraph, same wavelength. If S1 was real, it would be there. Not in exactly the same position. Planets do not hover in space like pinned photographs. They move along invisible tracks defined by gravity. But it should have shifted slightly. A subtle arc, a predictable displacement. That motion would transform S1 from candidate to planet. The data came in. The processing began again. Reference subtraction, noise modeling, artifact suppression. Astronomers know that excitement is dangerous. They approach follow-ups like skeptics. The new images resolved. There was Alpha Centauri's glare, carefully suppressed. There were diffraction patterns, familiar and chaotic. There was background structure, but S1 was not there. Not dimmer, not shifted, not even faint. It was gone. The first reaction in science is never drama. It is doubt. Perhaps the telescope misaligned slightly. Alpha Centauri moves quickly across the sky. Its proper motion is significant because it is so close. A tiny error in pointing could place the coronagraph imperfectly, altering sensitivity in certain regions. They recalibrated. They rechecked the offsets. They examined the instrument logs. Everything was within expected parameters. They looked deeper. Could the data reduction pipeline have suppressed the signal unintentionally? Aggressive subtraction techniques sometimes erase real objects along with noise. They ran independent processing methods. Alternative algorithms. Nothing. The region where S1 had once glowed was empty. In April 2025, they tried again. Astronomy rewards persistence. Webb observed under slightly different conditions. Alternative roll angles, different field orientations designed to change how artifacts manifest in the detector. If S1 had been hidden by a persistent speckle pattern, rotating the field might reveal it. The results arrived. Still nothing. At this point, excitement turns into something else. Silence. Because science has a memory. Astronomers have been here before. In the history of exoplanet detection, there are ghosts. Signals that shimmer briefly in data before dissolving under scrutiny. statistical fluctuations that masquerade as planets, instrumental quirks that trick even experienced teams. A 5 sigma detection sounds definitive. In particle physics, it often is. But in astronomy, particularly in high-contrast imaging near bright stars, systematic errors can imitate confidence. So the team did what responsible scientists must do. They tried to break S1 apart. They scrutinized the original August 2024 dataset again, this time with a colder mindset. They divided the data into independent subsets. If S1 was real, it should appear in each half. It did. They injected artificial planets into the raw frames at similar brightness and separation. The algorithms recovered them consistently, in ways that resembled S1. The statistical significance held, and yet, reality refused to cooperate. No planet appeared in February. No planet appeared in April. A simple explanation began to take shape. It had never been there. A statistical mirage, a rare alignment of noise peaks that survived internal tests but evaporated under new observations. This is not uncommon in cutting-edge astronomy. The frontier is noisy. Instruments operate at the limits of physical possibility. Coronagraphic imaging in the mid-infrared around one of the brightest stars in the sky is not a routine measurement. It is delicate. But there was a problem with the "it was noise" explanation. Noise does not usually behave so cleanly. The August 2024 detection had specific characteristics. Its brightness was consistent across multiple observing sequences. Its position was stable relative to Alpha Centauri A during the observation window. It did not drift like an asteroid. It did not smear like a cosmic ray. It looked like a point source, and now it was absent, which led to a more unsettling possibility. Planets move. Perhaps S1 had not vanished. Perhaps it had simply gone somewhere the telescope could not see. To understand this, you have to imagine the geometry. A coronagraph blocks the central star with a mask, a tiny opaque region designed to suppress overwhelming light. But that mask creates its own blind zone. Anything too close to the star's apparent position becomes invisible behind the suppression region. There is an inner working angle, a minimum separation at which the instrument can reliably detect companions. If S1's orbit carried it inward relative to our line of sight, it could slip inside that blind zone. From Earth, the planet would still exist, and it would still orbit. But Webb would see nothing, because the coronagraph would be blocking it. Think of it like a tiny moon crossing directly in front of a floodlight. You cannot see it, not because it is gone, but because it is swallowed by glare. The question became, is such an orbit plausible? To answer that, astronomers turned to simulation. They modeled millions of potential orbits consistent with the August detection. They varied inclination, eccentricity, argument of periapsis, every orbital parameter that determines a planet's path through space. They imposed one constraint. The planet had to appear where S1 was seen in August 2024. Then they asked a second question. Given that constraint, what fraction of possible orbits would place the planet inside Webb's blind zone in February and April 2025? Oh, the result was surprising. A substantial fraction, nearly half, of viable orbital configurations predicted exactly that behavior. Visible at one epoch, invisible at the next. Not because it vanished, because it moved, but there was more. The simulations suggested that if S1 followed an eccentric orbit, elongated rather than circular, it would spend part of its time far from the star, bright and detectable, and part of its time closer in, concealed by the coronagraph's suppression region. An eccentricity of around 0.4 fit the pattern well. That is not an extreme value. Many known exoplanets exhibit similar eccentricities. In our own solar system, Mercury's orbit has an eccentricity of about 0.2. Some comets reach far higher. An eccentric orbit around Alpha Centauri A would not be extraordinary. It would be dynamic. And then, someone noticed something even more intriguing. In 2019, ground-based observations had reported a faint candidate signal near Alpha Centauri A. It was labeled C1. That signal was never confirmed. It faded under scrutiny and was set aside as likely noise. But its projected separation from the star was not entirely incompatible with certain S1 orbital solutions. If, and it is a significant if, C1 and S1 were glimpses of the same planet at different orbital phases, the implications would be profound. That would imply an orbital period of roughly 2 to 3 years, which would mean something else: a return. If S1 followed that path, it should emerge from the coronagraph's blind region again sometime in 2026. Not speculation, prediction. And predictions can be tested. Suddenly, the disappearance of S1 was no longer a disappointment. It was a setup, because a false positive fades quietly. But a real planet on an eccentric orbit plays hide-and-seek with precision. The universe does not care about our schedules, but gravity is reliable. If S1 is real, it will return to view. If it does not, the hypothesis collapses. And so, Alpha Centauri A, silent for decades, became a ticking clock. Somewhere 4 light-years away, a world may be tracing a path we have only begun to calculate. It may be moving inward, slipping behind the star's glare, hidden but intact. Or it may never have existed at all. For now, we are left in an uncomfortable position, between detection and confirmation, between noise and discovery, between hope and restraint. And perhaps that is the most honest place science ever occupies. Because certainty in astronomy is not declared, it is earned, and in 2026, Alpha Centauri A will either give back what it briefly revealed, or it will remain silent. The difference between magic and physics is patience. If S1 were magic, it had already performed its trick. Appear, vanish, leave confusion behind. But if S1 were physics, if it were a real world orbiting Alpha Centauri A, then its disappearance was not mystery. It was geometry. Because planets do not blink out of existence. They move. To understand how something can be visible one month and invisible the next, you have to abandon the idea of a flat sky. What Webb sees is not a map. It is a projection, a 3-dimensional orbit flattened into 2 dimensions. Imagine a coin spinning in the air. From the side, you see its circular motion clearly. From directly above, it becomes a line. From certain angles, parts of that motion disappear entirely behind your hand. Now replace the coin with a Saturn mass world. Replace your hand with the overwhelming glare of a sun-like star. And replace your eyes with a coronagraph that blocks everything within a tiny radius of light. That is the stage. S1 was detected at a projected separation of roughly 2 astronomical units, about twice the distance between Earth and the Sun. But projected is the critical word. We do not know the true 3-dimensional distance. We do not know the tilt of the orbit relative to Earth. We do not know whether the planet is currently near its farthest point from the star, apastron, or plunging inward toward periastron. All we have is a snapshot. So, astronomers built universes, millions of them. They generated simulated planetary systems consistent with the August 2024 detection. Each simulation placed a planet at the observed position and assigned it a plausible orbit around Alpha Centauri A. Circular, elliptical, tilted, edge on, face on. Every configuration permitted by physics was tested. Then they ran the clock forward. February 2025, April 2025. Where would the planet be? In roughly half of the viable simulations, the answer was simple: hidden. The orbit carried the planet inward along our line of sight, reducing its apparent separation below Webb's inner working angle. From Earth, it would seem to dissolve into the star's suppressed glare. Not gone, concealed. This is the tyranny of perspective. In space, nothing is truly stationary relative to an observer. Motion and angle define visibility. Even in our own solar system, planets sometimes pass too close to the sun in the sky to observe safely. Venus disappears for weeks when it crosses behind or in front of the sun from Earth's viewpoint. Mercury is notoriously difficult to see for similar reasons. Now scale that to 4 light years. Scale it to a system where 2 sun-like stars orbit one another, perturbing gravitational stability. Scale it to a planet that may follow an eccentric path. The simulations converged on something intriguing. At an eccentricity around 0.3 to 0.5 reproduced the pattern well. Not an extreme orbit, not wildly elongated, just enough asymmetry that the planet spends more time far from the star, where it is slower and easier to detect, and less time racing inward, where it becomes lost in glare. In celestial mechanics, this is ordinary. In observational astronomy, it is everything, because it means disappearance is not failure. It is forecast. And then the timeline sharpened. If S1 follows an orbit of roughly 2 to 3 years, consistent with certain solutions linking it loosely to the earlier C1 candidate, then its next wide separation window should occur in 2026. Not randomly, predictably. That is the moment when science transitions from speculation to test. Because geometry does not improvise. And if the planet returns where gravity says it should, confidence skyrockets. If it does not, the hypothesis collapses under its own precision. But there is another layer to this story, one that makes Alpha Centauri far more complicated than a single star with a wandering planet. Alpha Centauri A is not alone. Its companion, Alpha Centauri B, orbits it with a period of about 80 years. At their closest approach, the 2 stars come within roughly 11 astronomical units of each other. At their farthest, they separate to about 35. That shifting gravitational influence matters. Planet formation in binary systems is not straightforward. The gravitational pull of a companion star can truncate protoplanetary disks, stir material, destabilize outer regions, and alter long-term orbital stability. For decades, models suggested that stable planetary orbits around Alpha Centauri A would likely be confined within a few astronomical units, perhaps less than 3, to avoid perturbations from Alpha Centauri B. S1's projected separation of about 2 astronomical units places it right in that theoretically stable zone, close enough to remain gravitationally bound to Alpha Centauri A, far enough to avoid immediate disruption. If real, its orbit would validate decades of modeling about planet formation in binary systems. But the binary also complicates observation. Alpha Centauri B contributes scattered light. Its own diffraction patterns contaminate the field. Its position relative to A changes slowly over time. Every observation of Alpha Centauri A is conducted in the gravitational and optical presence of its sibling, which makes the hide-and-seek of S1 even more delicate. Then there is the question of temperature. Based on mid-infrared brightness, S1's estimated equilibrium temperature falls between 220 and 250 Kelvin. Cold, comparable to Earth's average temperature, but likely without a solid surface, assuming it is a gas giant. At 2 astronomical units from a sun-like star, that temperature makes sense. Slightly cooler than Earth due to distance, but still within a range where icy moons, if present, could harbor subsurface oceans. That possibility changes everything, because if S1 is a Saturn mass world, it may host a retinue of moons. In our own solar system, Saturn's moon Enceladus ejects plumes of water vapor from beneath its icy crust. Jupiter's Europa hides an ocean beneath kilometers of ice. Gas giants are not destinations. Their moons might be. Now imagine that scenario orbiting the closest sun-like star to Earth. Two suns rising and setting in a binary sky. A gas giant circling every few years. An icy moon warmed not only by stellar light, but by tidal forces generated through orbital eccentricity. It is speculation. But it is grounded speculation. And grounded speculation is the birthplace of exploration. Still, everything hinges on geometry. Astronomy is often portrayed as discovery by surprise, unexpected flashes in the night. In reality, it is frequently discovery by return. The transit method confirms planets through repeated dips in brightness. Radial velocity confirms planets through periodic stellar wobbles. Direct imaging confirms planets through motion across the sky. S1 must move. That motion must be measurable, and it must follow Newton's laws. There is a certain poetry in this waiting. 4 light-years away, gravity operates with absolute indifference to our curiosity. The planet, if it exists, does not know it was detected. It continues along its orbit, obeying equations written centuries ago. Meanwhile, on Earth, astronomers prepare. Observing time is scheduled cautiously. Webb's instrument constraints must be respected. Coronagraph alignments must be optimized. The proper motion of Alpha Centauri must be recalculated with exquisite precision. The next attempt cannot afford ambiguity. Because if S1 reappears in 2026 at the predicted position, the implications will be immediate and profound. It would become the closest directly imaged exoplanet ever confirmed. Closer than Beta Pictoris b. Closer than any giant world seen in infrared glow. Close enough that future telescopes, 30-meter class ground observatories, space-based interferometers, could characterize its atmosphere in detail. Methane signatures, water vapor absorption, cloud structure, weather patterns. The nearest alien world, mapped not by inference, but by light. But if 2026 arrives and the field remains empty, then S1 joins the long list of astronomical ghosts. An artifact born at the edge of instrumental limits. A reminder that detection at the frontier is never simple. For now, Alpha Centauri. A holds its secret. The geometry is set. The clock is running. Somewhere in that system, either a planet is circling through a path that will soon carry it back into view, or there never was one at all. In astronomy, patience is not passive. It is the final instrument. And in 2026, geometry will answer. If it's real, everything changes. Not dramatically, not explosively, but fundamentally. Because for decades, Alpha Centauri has been a question mark hanging in the sky. The closest sun-like star system to Earth, and yet stubbornly silent. If S1 returns in 2026, that silence ends. And what replaces it is not just a planet, it is possibility. Let's assume, for a moment, that the simulations are correct. Assume the geometry holds. Assume that sometime in 2026, the James Webb Space Telescope peers once more toward Alpha Centauri A. And there it is again. Shifted. Exactly where orbital mechanics predicts it should be. At that moment, S1 stops being a candidate. It becomes a world, a Saturn mass gas giant orbiting at roughly 2 astronomical units from a star almost identical to our Sun. 4 light-years away. That distance matters. Proxima Centauri b, the rocky world orbiting the system's red dwarf companion, already holds the title of the closest known exoplanet. But Proxima is a flare star. Volatile, active, unpredictable. Its habitable zone lies extremely close to the star, subjecting any planet there to intense radiation bursts. Alpha Centauri A is different. It is stable, calm, solar-like. If S1 is confirmed, it becomes the closest known planet orbiting a sun-like star. That distinction is not cosmetic. It is strategic. Because future missions, whether space-based interferometers or direct imaging observatories, prioritize proximity. The closer the system, the larger the angular separation of its planets and the more detailed the observations we can make. A confirmed giant planet around Alpha Centauri A would immediately make the system a top target for atmospheric characterization. Methane, water vapor, carbon monoxide, cloud bands, storm systems. Even seasonal changes could eventually be resolved. And then there are the moons. Gas giants rarely orbit alone. In our own solar system, Saturn hosts more than 80 known moons. Jupiter, even more. Some are tiny captured rocks. Others are worlds in their own right. Titan with its methane lakes, Europa with its subsurface ocean, Ganymede larger than Mercury. And if S1 resembles Saturn in mass, it may host a miniature system of its own. Now imagine one of those moons, orbiting a gas giant, which itself orbits a sun-like star, inside the classical habitable zone. At roughly 2 astronomical units, S1's equilibrium temperature estimate, around 220 to 250 Kelvin, suggests a cold environment. But equilibrium temperature assumes no atmosphere, no greenhouse effect, no tidal heating. Moons can defy equilibrium. Tidal forces between a planet and its satellites generate internal friction. That friction generates heat. On Europa and Enceladus, tidal heating sustains subsurface oceans despite frigid external conditions. An exomoon around S1 could experience similar heating. Add starlight from Alpha Centauri A. Add reflected light from the gas giant itself. Add occasional gravitational stirring from Alpha Centauri B as it completes its slow binary orbit. The result is not guaranteed habitability, but it is plausible complexity. And complexity is where life finds opportunity. But S1's implications extend beyond astrobiology. They reach back to the beginning of planet formation theory. Binary stars were once considered hostile environments for stable planetary systems. The gravitational pull of a stellar companion can disrupt protoplanetary disks, truncate material, and destabilize outer orbits. Yet over the past 2 decades, we have learned that planets form in binary systems more often than expected. If S1 exists, it reinforces the idea that planet formation is resilient. That even in dynamically complex environments, gas giants can assemble, migrate, and settle into stable configurations. It suggests that the architecture of planetary systems is more flexible than early models predicted, and that matters, because binary stars are common. Roughly half of sun-like stars reside in multi-star systems. If planets can form and remain stable around stars like Alpha Centauri A, then the number of potentially planet-hosting systems in our galaxy expands dramatically. The silence of Alpha Centauri would transform into a statistical statement. Even here, planets thrive. But there is something else, something more subtle. If S1 returns, it will not merely confirm a planet, it will validate a method. High-contrast mid-infrared coronagraphy around extremely bright nearby stars is extraordinarily challenging. And the August 2024 detection pushed the James Webb Space Telescope near its technical limits. If S1 is confirmed, it proves that this approach works, that we can directly image planets in the nearest stellar systems, not just infer them indirectly through wobbles and shadows. It would mark a transition point, from detecting exoplanets statistically to studying them individually, up close. And then there is the psychological dimension. Alpha Centauri has always represented first. the first destination for interstellar probes in science fiction, the first star beyond our sun children learn by name, the first realistic candidate for a future generation of light-sail spacecraft. So projects like Breakthrough Starshot envision sending gram-scale probes propelled by lasers to reach Alpha Centauri within decades. Those probes need targets. A confirmed gas giant with potential moons around Alpha Centauri A would instantly refine mission priorities. Instead of flying blind into a stellar system, humanity would know there is structure there. A world. Possibly many. 4 light-years is still an enormous distance. At current spacecraft speeds, it would take tens of thousands of years to arrive. But technology evolves. The time between the Wright brothers' first flight and humans walking on the moon was 66 years. Alpha Centauri is not unreachable in principle. It is just beyond current capability. And knowing what waits there changes how we think about crossing that gap. But let's step back, because confirmation is not guaranteed. Science advances by resisting premature celebration. If S1 fails to return in 2026, if the field remains empty despite optimized observations, then we are left with something else. A boundary, a reminder of instrumental limits. The coronagraph's blind zone becomes a metaphor for knowledge itself. Sometimes, what we cannot see is not absence, but constraint. And yet, even a non-confirmation teaches us something. It refines models, improves processing techniques, sharpens statistical thresholds. The pursuit of S1 is not wasted effort regardless of outcome. Because astronomy is iterative, every observation builds on the previous. Every false positive calibrates caution. Every confirmed world expands understanding. But if S1 is real, then Alpha Centauri A is no longer a silent neighbor. It becomes a planetary system, one that may include inner rocky worlds still undetectable, one that may host outer debris belts sculpted by unseen companions, one that is close enough to become a laboratory for the next century of exoplanet science. Consider the scale of the Cenozoic era. 66 million years of planetary evolution on Earth since the dinosaurs vanished. During that time, mammals diversified, primates evolved, humans emerged, and technology accelerated to the point where we now detect heat signatures from distant worlds. We are the product of a long evolutionary chain that began in ecological vacancy and culminated in curiosity. And now that curiosity is focused on a star system that has always watched us from just beyond the edge of reach. If S1 exists, it has orbited Alpha Centauri A countless times since humans first learned to use fire. It circled while glaciers advanced and retreated. It moved silently while civilizations rose and fell. And only in the last few decades have we developed instruments sensitive enough to notice its faint warmth. There is something humbling about that. The universe does not announce its discoveries. It waits, patiently, for observers capable of seeing. In 2026, the James Webb Space Telescope will look again. Not in wonder, in precision. It will calculate proper motion corrections to fractions of arcseconds. It will align its coronagraph mask with millisecond accuracy. And it will subtract reference star patterns with algorithmic rigor, and it will either reveal a returning spark or confirm that the spark was illusion. Either outcome sharpens our understanding. But only one transforms Alpha Centauri forever. Because if S1 reappears, we will know something profound. The closest sun-like star to Earth hosts at least one planet, a real world, bound by gravity, radiating heat, circling in the dark, 4 light-years away, close enough that its light touches us in 4 years, close enough that future telescopes may map its atmosphere, close enough that one day, perhaps centuries from now, something we build might pass beside it. The Cenozoic era began with an extinction that reshaped life on Earth. And it continues now in an era where life on Earth reshapes how we explore the cosmos, from small nocturnal mammals beneath dinosaur feet to a species that detects faint infrared signatures from neighboring stars. Alpha Centauri A still holds its answer, and when it gives it, whether yes or no, it will not be dramatic. It will be a dot of light or an empty space. But in that dot, or in that silence, lies the next step in humanity's relationship with the universe. 4 light-years away, something is either circling or there never was. We are about to find out.